Hello everyone, my name is Nicolai and I will be presenting the work we have done on the paper titled Evaluation of Neural Networks for Residential Load Forecasting and the Impact of Systematic Feature Identification. My two co-authors are Zheng and Bo Nørregaard from the SDU Center for Energy Informatics at the Maersk Mc-Kinney Moller Institute at the University of Southern Denmark in Odense, Denmark. I will start my presentation by presenting the background and motivation for the study. Then I will take you through the methodology in the paper. Afterward, I will present the results, followed by the main discussion points, and finally I will conclude and talk about any future work this study presented. So, political decisions and ambitions are leading to new challenges for the energy system. Initiatives to reduce carbon emissions in Denmark include the construction of energy islands and investment in new technologies such as power to X and carbon capture. And in general, we want to be more green and we want the energy to be used efficiently. So for the distribution system operators, this means an increasing number of distributed energy resources they need to address and a higher need to maintain the quality of their grid. To help address this challenge, accurate predictions of the energy consumption can be forecasted using artificial intelligence methods. In the literature, researchers apply dozens of different variations of neural networks and machine learning algorithms, statistical models to reach the most accurate predictions. However, the supporting data that they use to forecast the electricity load is often taken for granted. Therefore, this paper studies the effects of systematically identifying and selecting relevant data to predict the electricity load using 4 types of neural networks. The methodology of this paper consists of 5 important systematic steps. First, an analysis of the target variable is conducted, which will lead to a better understanding of the forecast. Next, the supporting data is mapped using the CSTEP framework, which I will get into in a minute. And this will be used to identify any relevant data that could help improve the forecast accuracy. Then the features are selected based on their availability and their quality and the correlation with the target variable. There will also be conducted a feature importance analysis. Afterward, the models or algorithms used for the forecast are selected based on baseline performances. And finally, the selected models are then tuned on training data to get the best possible electricity load forecast. For the data analysis, the electricity consumption is sourced from 2 residential areas and is then aggregated to a total of 211 households. The dataset only contains pure electricity consumption, meaning any households in the area with PVs, electric heating, heat pumps, and EVs have been removed from the dataset to only have this pure electricity consumption. Each household's electricity consumption over 3.5 years was then clustered using an hourly daily load profile as the measure, and this can be seen from the image on the right here. We have 6 different clusters of different load profiles. The red indicates the average load profile within that cluster, and the gray ones are the actual load profiles of each household. Introducing the CSTEP framework, this is used to conduct this systematic approach. And we have used this framework to map relevant data to electricity consumption in 5 dimensions. You can see them here on the right. The first one is C, climate, environment, and geographic situation. S, societal, culture, and demographic environment. T, technology, infrastructure, skills, and technology readiness. And E, economy and finance. And finally, policies and regulations. Each of the dimensions can be focused on a general or specific level depending on the perspective. And finally, the data was also split into supporting, embedded, and exogenous data with an explanation of the possible impact each of them have on the target variable. So supporting data would be something like true measurements like from sensors, and embedded data would be something like weather, which can also be seen in the data, and the exogenous data is something we cannot put into a model. Then for the feature selection, step 3, we have now identified these CSTEP variables, and the data is then selected based on the availability and quality and correlation and importance. This process resulted in 4 relevant variables of high quality, which we then analyzed, and together with the aggregated electricity load, using a correlation analysis using the Pearson-R coefficient, and we also did feature importance using gradient boosted trees. On the right here you can see one of the features that we actually left out because we didn't think the quality was good enough. As you can see, the test data would be only very high electricity prices, which could be misleading for the model. Therefore, we left this one out. For the model selection, we chose these based on related works, and they serve to test this systematic approach on very popular types of neural networks for forecasting. And the 4 we have used for this study are a fully connected feed-forward network, a recurrent neural network, a long short-term memory network, and a gated recurrent unit. If these names do not make any sense, don't worry. The last 3 are simply variations of a neural network that specialize in sequential data, such as time series. The final step of the methodology is the model tuning, and here we simply have every single model undergo a tuning process to find the optimal hyperparameters to squeeze as much performance out of the models as possible. The tunable hyperparameters were split into 3 categories seen here on the right in the table, and after the tuning process the models are then used to forecast the electricity load, and the performance is validated on unseen test data. Each tuned model was then used to predict the next hour and the next 24 hours of electricity consumption. This was done to assess the flexibility of the model without changing any of the parameters. For each forecast, the supporting CSTEP variables were also excluded to examine the performance without this systematic identification approach. Finally, the models were used on data from electrically heated households to investigate if the composition of the aggregated electricity consumption has an effect. Looking at the 1-hour forecasts, they achieved an absolute error of around 4 kilowatt hours, or around 4.5% absolute percentage error. And here we see the forecast for each model in the first week of the testing data. On the graphs, the blue line is the actual aggregated load, and the orange the model's forecast. All 4 models have great performances, even during the peak and valley consumption hours, which are usually the most difficult parts to forecast. The highest errors are seen in between the morning and afternoon periods, where you see some very volatile patterns in here. The 24-hour forecasts are not as precise as the 1 hour, which is expected, but the overall percentage of the error of the 24-hour forecast is around 6.5 mean absolute percentage error. However, this proves that the models are flexible enough to be used for 2 different forecasting horizons, which is a very nice thing in a practical sense. Overall, the effect of the CSTEP variables were not considerable. So the highest increase in error was seen for the fully connected network, where when we removed the CSTEP variables, it resulted in an increase in absolute percentage error of around 2%. So that's the margin of error there. And however, the 24-hour forecast almost saw no change across all 4 models. And finally, the models were also used to forecast this electrically heated household data. And here we saw a very different picture with up to 15% in error depending on the model. And this experiment also showed that decreasing the number of households in the aggregation increases the error substantially. So because the sample size of the electrically heated households in the dataset was small, we validated this by then sampling an equal number of households from this pure electricity consumption dataset, which resulted in these bottom 2 errors in the table on the right, where the 14.33% error was achieved on the electric-based heating household data. And below you see it almost 11% error. It's for the pure electricity consumption data. So there are 5 main points of discussion of this paper. First of all, while the performance metrics show really good results, they can be rather misleading. The performance looks very similar when they're presented in a table and you only see a few variations, but when you're visually inspecting the forecasts on a plot, you can see a very different picture. And one model simply outperformed the others on very specific days, such as Christmas and during certain hours in the peak and valley hours. And this was a gated recurrent unit. It just performed the best visually when you plot the graphs and the predictions. Secondly, the composition of the data plays an important factor in the accuracy of the forecast, and this was proven by comparing the 2 different sets of data, where one was pure electricity consumption and the other one had only electrically heated households. And this addition of the CSTEP variables as supporting data did not have a substantial effect on the performance metrics. However, the systematic identification and selection of this supporting data has helped us better understand the target variable, meaning we can explain why the models forecast as they do more easily. And finally, the effect of these smaller sample sizes in the aggregated data were shown, and this may be due to the fact that the aggregated load becomes much more volatile as the number of samples decreases in the set, and they may have more varying peaks. Maybe one of the households has a peak in the morning and one in the afternoon, and then when you combine them all, they get kind of volatile, and as you increase the sample size, it gets more smooth. In conclusion, I have presented a novel systematic identification and selection of supporting data using the CSTEP framework prior to forecasting the aggregated electricity load of residential areas. This approach showed potential, but it did not show any substantial effect in our testing yet. However, this process did give a greater understanding of the target variable and domain, which can help curate better data in the future for researchers or actually for industry actors. The testing of several different networks indicates that choosing the optimal neural network architecture isn't as impactful as having really good data inputs. The findings of the study will be of interest to researchers who seek to make their data processing and analysis more systematic. For future work, we are planning to test the approach on more complex models with more complicated datasets of a larger sample size. And finally, we are planning on investigating ways we can improve these performance metrics of neural networks for time series forecasting, where we want to show a more realistic picture of the predictions. And if there are any questions or comments regarding this presentation or the paper, please reach out to me by mail. It's written here on the right below my picture. And thank you very much for listening.